All right, hi everybody. Welcome back to asymptotics and perturbation methods. We are moving now into a new phase of the course. We pretty much finished with talking about asymptotic expansion of integrals, and now we'll focus on asymptotic solutions to ordinary differential equations. Specifically, we'll start with the easiest kind, linear ordinary differential equations. But with the extra wrinkle that the coefficients, instead of being constant like they would be in a first differential equations course, we're going to do differential equations with non-constant coefficients. In other words, variable coefficients that depend on the independent variable, which we'll call x. Anyway, so this has a pretty rich asymptotic life, this part of the subject, and it'll occupy us for quite a while. All right, so let me begin. Okay. All right. So think of this as part 3 of the course. If part 1 was just what are asymptotic expansions and what are some of their properties, part 2 was asymptotic expansions of integrals. So now asymptotic analysis of linear ODEs. All right, so we'll start with, as I say, let me sort of think of it as a transitional topic. The connection between the integral representations that we've been looking at for things like Bessel functions or Airy functions. Later in the course, we'll see where they come up scientifically. But for now, let me try to make this segue from integral representations. How do I get an integral representation? Like, where did that integral that we wrote for the Bessel function J0, how could we derive that? That's something I promised I would show you at some point, and so this is that point. All right, so usually we get these integrals that represent special functions by doing a Fourier or a Laplace transform of some linear differential equation, and then solving for the transform, and then inverting the transform. That inverse transform will be in the form of some integral. So that's probably the most familiar place where this would come up. But another way to get an integral representation, I'm going to show you now to give us a derivation of this formula for J0. So here's Bessel's equation in the box at the bottom. This is one way of writing Bessel's equation. So you'll notice that I've got, it's a second order equation. I have a second derivative of y with respect to x, also a first derivative, and there's y itself. It is linear, right? Y is just appearing to the first power, and so are all its derivatives. So there's no like nonlinear functions of y. There's no sine of y or e to the y or y squared, or even y times y prime. Those would all be nonlinear terms. So it's just y and its derivatives to the first power. That's what linear means. But you can have functions of x in front of the coefficients, or in front of the y's, like we do here. And so this case is called, it's a special case of Bessel's equation. All right, now, and this object J0 that we've been talking about turns out to solve it. So here's how we could see that. First of all, when we have this linear structure of just, like a linear differential equation like this, the whole theory of linear algebra applies to such things. The solutions of this equation form a vector space. If you take the sum of two solutions, it will be a solution. And if you multiply a solution by a scalar, it's still a solution. So when you have linear and homogeneous, meaning 0 on the right-hand side, differential equation, you get all this nice vector space structure. And so here with this second order case, we know that we're going to have two linearly independent solutions to this second order equation, and they are called J0 and Y0. So I'm going to pretend that you've taken a good ordinary differential equations course and you've run into these objects in that course. This may not be true, but let's assume that you have. If not, you should have. Or if not, it's never too late to learn. So recall, kind of in quotes, that in that fictitious course that you may have taken, Actually, we do offer it in the junior year at Cornell for engineers if they want to take a math course after their first differential equations course. Anyway, so J0 is the solution of this equation that stays bounded as x goes to 0. Like the traditional way of dealing with this equation would be you could plug in a power series and look for a power series solution for the form of y, and then just pop that in and then calculate all the coefficients of those power series. And that will give you this nice, well-behaved function J0 that just approaches 1, or it stays bounded as x goes to 0. But you would find, if you did try a power series, that you're not going to be able to get the second solution just in terms of an ordinary Taylor series. And you need a little more sophisticated apparatus called a Frobenius series, more general than a Taylor series because it can allow non-integer powers of x, like square roots, or it can have logarithm of x, other things like that. So that's something that's traditionally discussed in this second differential equations course. And you would find that this other solution, y0, actually has a logarithmic singularity that causes it to go to negative infinity as y0, as x goes to 0. Okay, so that's, these are known facts, but all I want to do for now is just show you how you can derive this integral representation for J0, the one that stays bounded. So here's our strategy. We're going to look for a solution in the form of this inspired integral, something of the form e to the xz times some function p of z that we're going to choose to make it all work, integrated in the complex plane, the z-plane, on some contour c, which is something else that we're free to choose. So we're going to be at liberty to choose c and p correctly to make this work. And if you wonder where would such a guess come from, I mean, where would we ever think of such a thing? If you've studied Laplace transforms, you would know that the Laplace inversion formula sort of looks a little bit like this, an integral around some contour, something that looks like an e to the xz, and it's usually written e to the st. But anyway, it's the same kind of idea. So anyway, let's just try a guess of this type and see that it works. As I say, z is a complex variable. C is going to be a suitably chosen contour, and we'll see in the course of our calculation what it needs to be to make this work. All right, so let's try this guess. I think that's as much as I've written out ahead of time. And so now let's just try to take this object I've written for y and make it satisfy this differential equation up here. So to check, first I got to calculate y prime and then y double prime, and then I'm going to just substitute everything into that. All right, so let's do this using the fact that x is playing the role of a parameter here in this integral, and we can just, with abandon, differentiate inside the integral sign to calculate stuff like y prime of x. Differentiating under the integral, you get integral over c brings down a factor of z, e to the xz, p of z, dz. And then differentiating one more time with respect to x, bring down another factor of z, so z squared, e to the xz, p of z, dz. Right, I'm just differentiating the e to the xz. That gives me e to the xz again times the chain rule term of z. All right, so I've got that. And then when I substitute this into Bessel's equation, we'll see that Bessel's equation will be satisfied if, so, well, let's write it out. So we're trying to solve, we're trying to do, what was it, x, y double prime plus y prime plus xy equals 0, and now substituting all that stuff in there, this would be, well, you can notice everything is basically looking just like it's all integrated with respect to this p of z, e to the xz. The only thing that's changing is this term in front, the z squared or the z. So we could group everything together like so. Integral over c, x, z squared plus z plus x all of that stuff times e to the xz p of z dz. So Bessel is satisfied if this is 0. And we're going to try to arrange it so that this will be 0. And then we want it to be 0 for all x. All right, x was just a parameter in here. Okay, so this is a necessary condition for this guess to be a solution. Or necessary or sufficient? It will suffice. I guess it's necessary and sufficient. If our guess is correct, it will satisfy this. But so here's our strategy. Let's suppose, this is the first part that requires a little wishful thinking. Suppose we could find a function that I'll call s of z, such that the integrand becomes a perfect differential. By the integrand, I mean here, I'm thinking of this whole expression. That whole thing. Such that this integrand became find a function s such that the integrand becomes d dz of something. In this case, the d dz will be of e to the xz times this function that we're looking for, s. Oops, I left out the word find. That would be very nice. I mean, why is that so good? Let's suppose we could do that. Then what would happen? Then the integral, then Bessel's equation would become, well, I would have, since I've made it this way, d dz of something, e to the xz, s of z, dz, over this contour c. That would all, this is supposed to be 0. But if I'm integrating a derivative, I'm just going to get the values at the endpoint of this argument of the d dz. That is, I would just get e to the xz, s of z, evaluated at the boundary of this curve C. Right, that's the fundamental theorem of calculus, essentially. And so now, could I make that be 0? I mean, I would only, at that point, I would only have to choose if we could choose a C such that this holds, remember, we also have S at our disposal. We can choose S and C. But if we could, this, by the way, this is notation for the boundary of C if you're not used to it. So I'm thinking of C as having endpoints. So let's keep that in mind. I want to be able to make this work by a careful choice of either C or S or both. Okay, so now let's make everything work out. That is, going back, we had this earlier wish. We wished that this function S would have the property that d dz of this expression would equal this integrand. So let's write out what that condition is. That will determine S, in fact. All right, so far we want d dz e to the xz s of z to equal xz squared plus z plus x. I'm just copying the integrand. There was an e to the xz, and then a p of z. But all of this stuff, if I expand this over here, this would give me what? X e to the xz s of z, and also plus e to the xz s prime of z. Remember, I want this to be true for all x. So what's nifty about this is you can read off powers of x. If this is supposed to be true for all x, then like let me underline the things that have x's underneath them as prefactors. There's one, here's one, here's one. Oh, by the way, I can cancel out the e to the xz's everywhere. Right, so you can see that this could be achieved by having two conditions. If I equate terms, equate the coefficients of what are usually called like powers of x, meaning either x to the first power or x not there at all, then the two conditions are we get s of z from the underlined one in red, right? I mean, that one is going to give us s of z equals z squared plus 1, it looks like, times p. Right, that's from the coefficients of x. And then for the terms that don't have an x in front of it, like, let's do it in blue, like say this term and this, then let's see, so the blue guys are giving us s prime of z equals z times p, if I'm doing that right. Yeah, so that would work. Everything, I'm phrasing everything in the conditional here because again, it's if I can find an S and a curve C that will make everything work. But so far I'm still in business. And now you can see how to solve for S. You could divide the blue equation by the red equation and get a condition on S uniquely. So S prime over S is the P's cancel out and getting Z over Z squared plus 1. And remember, prime means derivative with respect to Z in this context. So I can integrate both sides with respect to Z, and I'm getting, I mean, it's separable, right? This is log of S of Z. The right-hand side integrates to 1/2 log of Z squared plus 1. And then there could be plus constant, potentially. But in some problems, you might need it. Here, it turns out I can get everything I want by setting this constant to 0. So I'm not going to dwell on, actually, maybe I won't say it that way. I can get this J0 solution I'm looking for by choosing the constant equals 0. If we wanted to, sorry, yes?
Do we need to worry here about P of Z being equal to 0?
Well, potentially you could, yes. That could be a concern. Yeah.
Oh, okay. And what would
Potentially,
you
you'd
do
have
with
to
it?
watch out for P of Z being zero. We're going to see momentarily that P of Z will not be zero.
Okay.
But actually, it could be zero at certain points. So, but it won't be identically zero. So yeah, you're right. You should keep your eye. Maybe we should say, let's assume P of Z is not zero for now. I mean, if P of Z is zero, what would happen? Then S would be, I mean, are you saying P is identically zero or just particular points?
Particular point.
Some particular points, yeah. Well, yeah, at those points, S could potentially be zero, I suppose. So we'll
But
sort of,
that's not
for
a
now,
problem, right?
Sorry, what's that, Maria?
S equals to 0 is not a problem, right?
It wouldn't be a terrible problem. It wouldn't be super useful for us necessarily. I mean, if it were identically zero. If it's zero at some points, that may not cause any trouble.
Okay.
Yeah. Well, so, but yeah, you're right. For now, we should note that we've been assuming when we divided through, we assumed P was not zero. Okay. So, but anyway, I was just going to make this point that I'm going to just ignore this constant. If I want to, I could keep it and see what it would imply, but I don't really need it. So making life easy, then solving for this S of Z, I'm going to get that S of Z, because remember, I'm not looking for the most general solution. I'm just looking for some integral representation of J0. So anyway, peeling off the logarithms, you can see this says that S of Z is natural log of Z squared plus 1 to the 1/2 power. Oops, I don't want that logarithm. That's the whole point. I can get rid of that. Did I do that right? I think so. Yeah. So in other words, oh, actually, why am I laboring with all those brackets? Don't need that either. It's just that. Right. Or in other words, it's square root of Z squared plus 1. So as you can see, S could potentially be 0 at the points plus and minus I. But let's see what P comes out to be. I mean, what was our P? The condition on P, if I look above, was that that's coming from this red equation here. P of Z is S divided by Z squared plus 1. So this would be that will give us a 1 over a square root. So that's not going to be 0 except at Z equals infinity, I think, right? Yeah. So you had asked about dividing by 0. So it looks like we're not, in the finite plane, we're not going to end up dividing by 0 with this P. Okay. And so where are we so far? So what we have is that this y of x, if I write y of x is the integral over c of e to the xz, 1 over square root of z squared plus 1 dz. We know that this satisfies Bessel's equation. But remember, we had that earlier caveat. If we can find a C, contour, C, the condition was we wanted e to the xz times s of z on the boundary should give us 0 for all x. So what is that S? I mean, let's remind ourselves. It's e to the xz. Just a minute ago, we said S was the square root. So I want that on the boundary of C to equal 0 for all x. And so now you can see how to pick the contour. right? I mean, if I just make that square root be 0 at the endpoints, that would take care of it. So one way that would work is choose a contour that goes from minus I to I. And that will take care of it. Now, a very simple choice would be just a little vertical line segment. Say, say if there's I and here's negative I. You could pick any contour, but a good one is to just pick something that looks like that. At least this one will give us the standard integral representation of Bessel's function J0. So let's see what this does for us. What we're saying is, if I do that, then when I substitute back for my expression for y of x, maybe this deserves a box. If I take that y of x and do the contour I just said, so let's rewrite z as I times some other variable. Let's say z equals IW. Where the W goes from 1 to -1. Then my integral becomes it was minus I to I, e to the x z dz over square root of z squared plus 1. And with this change of variables, it's now from -1 to 1. So I'm representing z as IW, so this becomes I WX. The dz is I dW. And the denominator, which had been z squared plus 1, now becomes 1 minus w squared inside a square root. If I've done that right. Okay. So let's try to understand what the relationship of this thing is that we've constructed to J0 and Y0. We know that this satisfies Bessel's equation. That only tells us it could be some scalar multiple of J0, could be some scalar multiple of the singular one, Y0, or it could be a linear combination of the two of them. What is going on here? So one way to tell is just let's see what's happening at the origin, because that's what distinguishes the two cases, the Y0 and the J0. And so if you look at Y0, just plug that in, you'd have integral from -1 to 1, substituting x equals 0, that exponential just becomes 1. I have an I out front, dw over square root of 1 minus w squared. So that's an integral you would have learned in your first calculus course that involves arc sine. Or you could just do a substitution, w equals sine theta, and you'll get that. So this comes out to be, if you want, a little substitution there if you can't remember it. But anyway, you end up getting I times pi. And notice that that's bounded. It's not going to infinity. And so that's telling us that the thing we've just constructed is some scalar multiple of J0. It doesn't have any singular part in it. If it did have any Y0 in it, it'd be blowing up. So this thing that we've just written down, the y of x is some constant, let's say A times J0 of x. And since J0 of 0 is 1 by definition, whereas Y0 is just A, but we've already decided Y0 is also I pi. So that's telling us what A has to equal. And so I've just somehow managed to derive y of x is I times pi times J0 itself. But this y of x was this integral I wrote up here. Well, there too. So let's see. When you put everything together, maybe I should just go here. The conclusion after cleaning up this stuff is that we've just derived the representation J0 of x is 1 over I pi times the object I was calling y of x. So canceling out factors of I get 1 over pi integral from -1 to 1 e to the ixw dw over the square root of 1 minus w squared, which is an interesting integral representation of J0. It's not the one exactly that we're used to. It's pretty close, but it's not the one we're totally used to. You can observe, though, that since this really has a real and an imaginary part, right? The e to the ixw, there's a cosine plus an I sine, and the I sine integral will vanish because this is an even expression in w, and sine of xw would be odd in w. Notice we're on a symmetric interval from -1 to 1. So the imaginary part will cancel out, and this is just going to reduce to 1 over pi, something that's manifestly real, as it should be, cosine of xw dw all over square root 1 minus w squared. So that's a nice representation of the Bessel function. Now, I don't know. You could do a little more manipulating to make it look like what we're used to. Maybe I'll just do those steps. So here would be the steps. You could say, well, this is also twice what I would get if I integrated from 0 to 1. Cosine xw dw over the square root 1 minus w squared. And then let's let w equal sine t to recover the form that we're used to. So if I do that, then dw would be cosine t dt. And this whole expression becomes 2 over pi. I'm now doing a t integral, so it's from 0 to pi over 2. And then in here, I'm getting cosine of x sine t, which looks familiar, and then cosine t dt, but the square root is itself giving a cosine of t down here. So those cancel. And so we're getting something that really looks very close to what we had been using in the course. Cosine x sine t dt. It's slightly different than what we had, but that's just because you can show, our usual integral goes from minus pi over 2 to pi over 2. or no, I guess it was usually from 0 to pi. That's the way we usually did it, rather than 0 to pi over 2. But if you want, you can show the integral from 0 to pi over 2 of cosine xt, x sine t dt, is the same as the integral from pi over 2 to pi of cosine x sine t dt. You can check that if you want by use yet another substitution, u equals pi minus t, to check. So what I'm saying is I've got twice of the 2 copies of this integral from 0 to pi over 2, and I can just replace one of them with this integral from pi over 2 to pi. And so the whole thing comes down to J0 of x is what we said from the beginning, 1 over pi, integral 0 to pi, cosine x sine t dt. That's what we wanted to prove. Okay, so that was a long harangue just to show you how you could derive the Bessel function. So you want to ask anything about any of the steps in there? There is a natural question you might think to ask. So I wonder if any of you will.
Going back to what Maria was talking about, our 2 endpoints are at z equals I and minus I, and p of I and minus I is 0 at the endpoints. Are we still?
Wait, is that true?
I think so.
P or S?
P.
I think P is not 0 there.
P is, well, infinity, right? Because it's 1 over square root of.
Never mind. Sorry there.
So P is not 0. There's no problem with P being 0. There is a little problem with P looking like it's blowing up. At the endpoints, it does look like I'm blowing up there. So I'm not sure what to say about that. I mean, maybe we should think of that we're satisfying the differential equation on the interior of the line segment, but not at the endpoints. That may be good enough. Yeah, I mean, I think we are creating some singularities at these endpoints, but they're integrable singularities, and they're not causing any problem in the definition of J0, turns out. So yeah, there's a bit of looseness in this argument, but that's the way we do it. The thing I was thinking you might ask, though, is what if I wanted an integral representation for the other kind of Bessel function, for the Y0? How could I get that? And that's a bit harder. And I don't want to talk about it, but I can post something. So in the book by Olver, his book, maybe I'll just write a little reference, because this question has come up in previous years. So I'll just record for posterity for if you want to learn how to do an integral representation of that singular special function that satisfies Bessel's equation. See the book by Olver called, let's see what it's called. I actually have it here. Intro to Asymptotics and Special Functions. So he does this on page 241 to 43. And it involves a more complicated contour. But anyway, that book is, if you want more rigor, by the way, than what we're doing in this course, I would recommend that book. It's quite rigorous and careful. Very different in spirit from our treatment. Okay. All right, so I'm going to leave that. Oh, look at that. And I'm just where I want to be. How nice. Okay, so we're now done with integrals for a while. And now we're moving into this part of the course. We've made the transition into now thinking about second order linear differential equations with variable coefficients. You can read about this in Bender and Orsag in chapter 3. The whole chapter is devoted to that. And when they say local analysis, this means in the neighborhood of some point. Like it's all controlled by the infinitesimal neighborhood of some point that we're expanding around using some kind of series expansion. And our goal is going to be to understand the asymptotic behavior of a solution to that differential equation directly from the equation, not by going through an integral representation of the solution. Just look at the equation, and almost by magic, you can read off how y of x will behave close to the point of interest. So it's pretty magical. It's in some ways easier than dealing with integral representations, but the downside is that we will get the dependence on x, but we won't get a prefactor. We won't know the constant. Like we'll know a constant times some function of x is the functional behavior close to that point asymptotically, but we won't know the constant. If you actually want that constant, then you have to have more information of the type we had when we did integral representations. But often this is good enough if you just want to understand like scaling behavior and that type of thing. Okay, so the class of differential equations that we're going to be looking at, as I say, are the second order. So notice the highest derivative is this second derivative. They are linear. As I said, y and its derivatives only appear to the first power only. They're homogeneous equations. I've got a 0 on the right-hand side after I put all the y stuff on the left-hand side. So no functions of x over here. And finally, I've got these variable coefficients, which following Bender and Orsag, they start numbering from the coefficient of y. So this one is called P0 of x. The next one is called P1 of x. And there's no loss in generality in getting rid of the coefficient of the y double prime, because if I had one, I could just divide it through and it would go in here and in here. So we'll just write it like this. So second order linear homogeneous with variable coefficients. Bessel's equation can be put in this form, Airy's equation, something called the parabolic cylinder equation. A pretty broad class of interesting equations here. They come up a lot, especially in quantum mechanics, but in other fields too. All right, so we're going to be looking at those. And as I mentioned earlier, we have this whole vector space formalism. Since it's linear, we can write the general solution as a linear combination of any two linearly independent solutions, which we'll call y1 and y2. Okay. So how do we generate those linearly independent solutions would be our question. And the answer is it kind of depends. This whole story is going to depend on the nature of these two functions, the P1 and the P0. And it really depends on how nasty they are near the point that we're expanding around. By nasty, I mean like, are they analytic functions? That'd be the very tamest, nicest possible behavior. Could they have singularities like poles or branch points? If so, what's the nature of any singularities in those functions P? All of that controls what Y can do. So there's a whole big story about this. This is in that mythological second course on differential equations. You would learn this when you do the chapter on power series solutions of differential equations. So again, I'm going to pretend that that's a review. If you need to review it, you could read the book around page 62 of Bender and Orsag. They go through pretty quickly, but you may want to look at some other textbook on differential equations if you haven't done it before, this topic. Okay, so here are the three types of things that can happen in order of increasing excitement and horror. So the least horrifying and the dullest is if you just have an ordinary point x0 and you expand around that. Now what makes it ordinary is that these coefficient functions P0 of x and P1 of x are just as nice as they could be if those are analytic functions in some neighborhood around x0. Could be a tiny neighborhood, but as long as they're analytic in some little open set around x0, then you have an ordinary point at x0. Now, by analytic here, I'm not really talking about complex variables. I am actually, but if you're just thinking in terms of real variables, analytic would mean that these functions of x have convergent power series. They can be represented as a simple Taylor series around x0, and that series will converge. So if we have that, if we have a convergent power series, then we just plug in a guess for y that's itself a power series, and everything will work, and we can calculate y that way. So if you do that, then your solutions y will be expressible as convergent Taylor series. So this is a traditional theory. Nothing to it. You just do it and it will work. The only thing to it is to prove that the resulting solution is convergent. And so it's that kind of math. So I'm going to skip it. Similarly, it turns out that the theory works even if the p's are a little bit singular. As long as they're not too singular, you can do the same kind of thing with power series. This is a little more sophisticated. It's when you're dealing with a point that's not an ordinary point, but you can say it this way. The function p1 is no more singular than 1 over x. It's sort of behaving like 1 over x minus x0, or not even that singular as x approaches x0. So the slick way of saying it is, if x minus x0 times p1 is analytic, and if p0 times x minus x0 squared is analytic. So in other words, this one doesn't have any worse than a 1 over x singularity, and this one doesn't have any worse than a 1 over x squared singularity. If you have both of those, then it turns out, after a big theoretical development, you can show that the solutions to such problems around regular singular points can be expressed not in terms of a Taylor series, but a generalization called a Frobenius series. So that's like 2 weeks of work in a differential equations course to show that. And it's Frobenius series are like Taylor series, but as I mentioned earlier, they're a little more general in that they have they allow for non-integer powers of x. You can have, like 1 over, you can have square root of x, you could have x to the 1/3, that type of thing, or even x to an irrational power. And you can also have natural logarithm of x and so on. So there's a specific form that the solutions take that makes it qualified to be called a Frobenius series. And this whole thing is worked out in the book around page 63 and also in later sections. And so this is a very classical theory from the 1800s. And I'm not going to talk about that either because these things have a whole big apparatus for dealing with them. The interesting case is when it's neither of the first two. If you have an irregular singular point, so neither of the above, then, as Bender and Orsog emphasized, there's no general theory for this case. This is the Wild West. Even for linear differential equations, crazy stuff can happen. So there's no general theory, and this is the case that we want to focus on. And so I just want to now show you an excerpt from the book that I found very charming. I love this book by Bender and Orsog. If you're not reading it, you should. These guys are delightful writers, I think. So here's an excerpt when they start talking about the local behavior near irregular singular points. They've just gone through in the book, so that we're in section 3.4. They mark it as E, meaning it's an easy section. They also have I for intermediate and A for advanced. So you can always tell what you're reading by just looking at, oh, this is an easy one. Okay, so they say, and you can see I like to write in my books. I've marked it with a little blue asterisk. They say our analysis of ordinary and regular singular points, which they've just gone plowing through in earlier sections, they say that's fundamentally different from the asymptotic analysis to be used throughout the remainder of this book. I love this part. The approach of the last 2 sections has been prosaic and heavy-handed. The series were convergent. The manipulations were mechanical and rigorous. The treatment was thorough to the point of being devastatingly boring to us. And they say, this mummified style, man, how often do you see in a math book the word mummified? This thing is so dead, it's like a mummy. It's been dead for thousands of years. It's not true, though, only 100 years. This mummified style reflects the completeness of the theory. There was no room for imaginative mathematics. Okay, so that's their taste. But then they say from this point on, our style changes. They're going to now be analyzing behavior near irregular singular points. And we're forced to develop entirely new tools. And they then say, although it's possible to justify the use of these tools on a rigorous level, they're not going to do that, and neither am I. Such justification makes for slow reading and is contrary to the spirit of this book. Our intention is to omit time-consuming rigor and to emphasize careful problem solving. Okay, so that's an interesting distinction, not just that the opposite of careful is careless, or the opposite of rigor is careless and sloppy. They're careful, they're just not rigorous. Okay, they don't prove everything, but they are paying careful attention. So anyway, they say in contrast to the methods of the last two sections, which we would describe as exact, rigorous, systematic, limited in scope, and deadly, meaning deadly boring, these new methods are approximate, intuitive, heuristic, meaning they help you find the answer, very powerful, and fascinating. All right, so I'm going into all this as just a case for the spirit of applied math, for those of you who have taken too much pure math and are led to think that's the only style there is. I'm sure by now you know I don't adhere to that style. So yeah, so they're singing my song, or I'm singing their song or something. Okay, anyway, feel free to disregard all of that if you don't like this approach, but if so, you may be in the wrong course. So anyway, let's get back into the math. So let's start talking about an example. I mean, I've given you the cases. Let's see if we can recognize. I mean, it's important to be able to recognize, do you have an irregular singular point or not? So let's see. Suppose I had this equation, something of the form x to the n, y double prime, plus xy prime plus y equals 0, where here I'm thinking of this number n as something greater than or equal to 0, and it's an integer. And the question is, what kind of point is the origin? So I guess earlier I was calling it x0, but whatever. All right, let's just call it that for now. It's some kind of point. Now, what are we supposed to do? Or, you have to look at, I suggested looking at it as my coefficient of y double prime is supposed to be 1. So this would give me plus x to the 1 minus n times y prime plus x to the minus n times y equals 0. And we said that we have an ordinary point if these, we have to look at these coefficients. We don't want those to be singular at all. I mean, they should be analytic. So what powers of x would give me something analytic in both cases? Well, I better not have any negative powers of x, right? So I'm going to get an ordinary point if that'd be an ordinary point if, so what do I need? 1 minus n should be greater than or equal to 0, that exponent. And I also need minus n to be greater than or equal to 0. So what am I doing? I want to conclude n equals 0. Oh, I'm sorry. I meant to, yeah, because I assumed n was greater than or equal to 0 to begin with. Right. So the only way we get an ordinary point is n equals 0. Can I get a regular singular point? Yes. Turns out you get a regular singular point if n equals 1 or 2. You can check that because this term will not be, this one's not more singular than 1 over x squared, and this one's not more singular than 1 over x in those cases. And then if n equals 3 or higher, you get an irregular singular point. All right, so that's just a little example. Let me also show you something that occasionally comes up, which is sometimes, we've been expanding around x equals infinity frequently in our asymptotic expansion of integrals. And we'll want to think about the behavior of a differential equation out at x equals infinity. And so we want to know, is the point at infinity, what kind of singular point is out there? That's a question that will frequently come up. So as an example of such a thing, let me show you how you could classify the singular point at x equals infinity for Airy's equation. We haven't really talked yet about Airy's equation much in the course. It will be coming up later. But here's what it looks like. It's just a very nice little equation. Y double prime is xy. Notice the variable coefficient of x there multiplying y. So it's confusing in a way. If the first time you look at it, you think, what's going on here? I mean, just intuitively what's going on is if this x is a positive number, this thing will behave sort of like something that has exponential growth or decay, right? If it's y double prime equals something positive, like say if it were y double prime equals y, that would have just exponential growth or decay, e to the x or e to the minus x as a solution. If x were negative, then you get oscillatory solutions because this thing acts sort of like a simple harmonic oscillator. It looks like it has sines and cosines, kind of, as solutions, if this were y double prime is negative y. Of course, none of that is correct because you can't treat x as a constant. X is the independent variable. But it's sort of right in that you do get kind of like exponential behavior on one side of the x-axis and kind of like oscillatory behavior on the other side. But getting that really nailed down is what we'll do later. Anyway, for now, let's just see what happens out at x equals infinity. The way that you approach something like this is to bring infinity into the origin by changing variables. So the standard move is bring infinity into the origin by saying let t equals 1 over x. And then classify t equals 0. And that'll give you the nature of the singular point at x equals infinity. So that kind of change of variables goes like this. dy dx by the chain rule, I have to convert all my derivatives to t derivatives. So dy dx is dy dt, dt dx, which I'll observe dt dx, that's giving me a minus 1 over x squared. And dy dt, I'll use the notation y dot. So dot will mean t derivative. And the 1 over x squared, now since we're converting things into t, you could think of as negative t squared. And then that's times y dot. So that's the rule for how you convert y prime into y dot. And similarly, we could convert y double prime. Maybe I'll let you check that on your own. Well, no, I'll just write it. So that would be d dt of minus t squared y dot. So that's d dt of y prime, but then I have to do dt dx to make this really an x derivative. And so I'm getting t squared d dt of t squared y dot. And when you write that out with the product rule, you get y double prime is t to the fourth y double dot plus 2t cubed y dot. Okay, so then substituting everything into Airy's equation, which was y double prime is xy, that becomes t to the fourth y double dot plus 2t cubed y dot is 1 over ty, because this is xy, and this whole thing is y double prime. So now we put that in the standard form by making y double dot all by itself, y double dot plus 2 over t y dot minus 1 over t to the fifth y equals 0. And so let's stare at that. The test is, we're trying to see, do we have an irregular singular point or a singular point at t equals 0? So first we observe this is not more singular than 1 over t. So it's still in the running to be a regular singular point. But this is much more singular than 1 over t squared. That's 1 over t to the fifth. So this is an irregular singular point. So and therefore the same is true at x equals infinity. Okay, so Airy's equation has a singular point out at infinity. And a lot of our examples will. All right, so I'm going to finish now with showing you how you can try to analyze behavior near an irregular singular point. This will be our first taste of something we'll be doing a lot in the days to come. But I think we have 10 minutes. We can start on this. So we're not going to get an exact solution. We're going to get an asymptotic expansion of y near an irregular singular point for this class of problems. These second order linear ODEs with variable coefficients. So the strategy that Bender and Orsog advocate and that we'll be using is to essentially always try something of the form y equals e to some function s of x. That's an ansatz, so we'll just make that guess. And then we're going to calculate y prime and y double prime with this guess. So y prime, if we do this, would be s prime e to the s of x. And y double prime by the product rule will give us s double prime e to the s plus s prime, and then squared, because there's another one being pulled down, e to the s of x. So it's convenient to write this as s double prime plus s prime squared, all times e to the s. The reason for guessing e to the s is that when we plug that in, all the e to the s's are going to cancel out, and we'll just get an equation for s that is relatively tractable by asymptotic reasoning. So we're going to examine the resulting ODE, ordinary differential equation, for s. And usually something asymptotically nice will happen. Not always, but we'll see counterexamples. But usually s double prime will be very small compared to s prime squared in that square bracket above. So we're going to start neglecting terms, hoping that other terms are asymptotically dominant compared to them. And that's how we'll get our asymptotics. So let me do an example to show you how this would work. I think we can get started on it. I'm not sure I can finish it, but let's see. This one's a little bit contrived, but maybe it's good. Anyway, x to the fourth, y double prime, plus 2x cubed y prime minus y equals 0. There's an equation of the type we're interested in. Turns out it has an irregular singular point at x equals 0. You can check that it does. And here's the part that's amusing and why I say it's contrived. This has been cooked, this question, to have exact solutions that we can just write down. This would not normally happen. But it actually has exact solutions that are e to the plus and minus 1 over x. You can just plug that in and you'll see it will work. And you can see that those will be very singular as x goes to 0. This has an essential singularity at x equals 0. So it actually has exact solutions, but let's pretend we didn't know that. Let's see what the method would give us. Suppose we didn't know this. Because in our typical problems, we won't have exact solutions and we won't know. Okay, so then if we try the ansatz y equals e to the s, then doing the stuff that I just wrote down for the second and first derivative, you would get x to the fourth. The second derivative stuff would give you s double prime plus s prime squared. My equation said go 2x cubed, substitute for, then here I have an s prime, and then minus 1. The whole thing would be times e to the s, and that would equal 0. And of course, e to the s is never 0, so I can cancel that out. And so I'm left with just trying to understand this equation for s double prime plus s prime squared plus 2s prime over x minus 1 over x to the fourth equals 0. So I want to try to figure out what's going on with that for x near 0. And the argument that we would make is what the book refers to as dominant balance. You try to compare the size of the different terms for x near 0. So the idea of dominant balance is we're going to assume two terms balance each other as x goes to 0 in this case, or in general as x goes to the point of interest that we called x0. Assume that there are two big terms that balance each other and the other terms are asymptotically smaller. As x goes to 0. And so we just try to identify what are those two dominant terms. And we have to check for consistency. So I'll show you a couple ways to do it. Next time I'll show you a graphical way to pick out the dominant balance, but a brute force thing would be you could just try stuff and see what works. So for instance, there's a lot of combinations. If you stare at them, you can see this 1 over x to the 4th looks like it might be big. That's a pretty big singularity. So you might think that's a contender. So let me try comparing this to each of these in turn and see what happens. Like maybe this is one of the big ones and one of these is one of the big ones, but which? So let's try A. What if I balance the last two? Like maybe it's this one balancing this and these two are much smaller. Let's try that. It's not going to work, but let's see why not. So if I balance the last two terms, what would that imply? That would say 2 over x, s prime would be asymptotic to 1 over x to the 4th. Now here we're going to, when we have an asymptotic relationship like this, we're allowed to integrate both sides. It'll still be asymptotically true. Integration is a very mild operation I mentioned earlier in the course. So we're also assuming, as I said, that all other terms are much less. Let's check if that's correct. Well, if it is, so this would say that s prime is of the order of 1 over x cubed. Or I'm not worrying about the 2. Right, it would be big O of 1 over x cubed. And so integrating that, let's compare now. How big are the other terms? One of them was s prime squared. That would be order 1 over x to the 6th, which we already see we're in trouble. That's much more singular than 1 over x to the 4th. So this whole thing is inconsistent. This is much greater than 1 over x to the 4th. Okay, so that's no good. Let me just tell you, I don't want to keep you too long over time. If you balance the first and last, that would mean you'd be comparing s double prime to 1 over x to the 4th. I'll let you check that. That also comes out to be inconsistent. So check. Check that for full understanding. Let me show you what it looks like when it works. If I balance the second and the last term, then I would be saying maybe s prime squared is the one that balances 1 over x to the 4th. If that were the case, then this would be saying that s prime would be order 1 over x squared by taking square root of both sides. Well, yeah. Now, what about that? Actually, yeah. So that would then say, well, if I then compare the other terms, well, one of those terms was s double prime. That would then be of order 1 over x cubed, which is looking good because that is much less than 1 over x to the 4th. And what other terms are there? There was also a term 2 over x times s prime. How big would that be? So that's also a big O of 1 over x cubed, right? Because we said s prime is order 1 over s x squared. So that's also working. So this whole thing is consistent. And once we've observed that s prime is of that order, well, actually, we can just solve for s prime. I mean, using this asymptotic formula here, those are the dominant terms. And so s prime, taking square root of both sides, is plus or minus 1 over x squared. And so then integrating that, you can conclude that s of x is asymptotic to minus over plus 1 over x, which is what we said, because remember at the beginning, I told you e to the 1 over x and e to the minus 1 over x were exact solutions. Normally, this would just be a first approximation to the correct answer. Here it's actually exact. So like I say, normally this would be our first approximation to s of x, but here it's exact because of the problem being contrived. Okay, so next time I'll show you, when I say it's our first approximation to S, what we're going to want to do is churn out a bunch of terms in S, not go beyond the leading order approximation and get several terms. And that will give us not just an asymptotic approximation to S, but to the function y itself, which is the thing we're interested in. We're interested in the solutions of the differential equation. And so we'll get an asymptotic behavior for y if we go out far enough in S. So I'll show you that next time, and see you then.